Okay, welcome back to what I believe should be lecture number 4, wireless without batteries. Here's my rough outline for today. First of all, you'll notice that I had a senior moment and I forgot our course number. Thank you, Buzz, for correcting me. And then here we have kind of a rough outline of what I want to start talking about. We're going to do today, we're going to talk about some administrative things, homework, some of the like. I'll repeat some of the deadlines that we've talked about. Next I want to just talk about an application for a little bit. We don't appreciate the fact that even though what we're studying is kind of cutting edge electrical engineering, wireless without batteries, low energy wireless, energy harvesting, passive wireless, and the future is bright. Like the biggest things are yet to come in this field. There are actually some commercial success stories that employ this technology that are well established and already a success in their own right. So we're going to talk about one of those, automatic vehicle identification, or AVI. This was conceived of back in the 70s. Actually, there were some articles even published before then, but people really in earnest began to develop them in the 70s, deploy them in the 80s, and hone them in the 90s and 2000s. And you can see these in all sorts of cities, usually in the form of RFID toll tags, but there's some other interesting technologies there as well. So we'll dissect a system. What does a realistic system look like? And then we'll get to the meat of the lecture today, which is exotic rectification and limits. Rectification, energy harvesting using exotic devices, not just plain old diodes, but ways to increase the efficiency of the way that these things harvest. What are some of the promising technologies, and what's the fundamental limit of conventional diodes? And then we'll see what else. We might do a prelude to the next topic in the class, but I suspect we'll probably run out of time by then. Okay, so administratively speaking, here's what's going on. Homework 1. Which is embarrassingly easy, right? Have you taken a look at it already? It's not that hard. Homework 1, it's due this Friday. I don't care what the time is. We don't actually physically meet here in Shenzhen, so as I said, slip it under the door, submit it electronically. Give it to me if you see me, although I don't think I'm actually going to be in here on Friday. And if you're not here on Friday, that's okay too. Just take a picture with your phone and email it to me. And for the video students, this Friday is the 20th. Video students, distance learning students, will have until the 27th to submit it electronically. Ah, yes.
So both hard copy and soft copy are accepted? Or
Yeah, either one, whatever you want. And I will likely assign homework number 2 tonight or tomorrow morning, and that will be due next Wednesday. I will need to sneak a copy. It'll be the 25th, I think. Distance learning students, it will be February the 1st. First or second? First. And I'm trying to sneak in. Then you won't get a homework for about a week because I'm trying to sneak this in before Chinese New Year. Our lecture class here does not meet after next Wednesday for all that following week as well. So it'll be almost maybe 11 days between lectures. So you'll get a reprieve if you're watching this on video after next week. But then you'll have to watch stuff during Georgia Tech spring break. So it's taking your break early. And as I mentioned earlier, if you want to know the date for test number 1, Test number 1 is going to be on Monday, February the 20th. Still quite a ways away, but just something to keep on your planning schedule. And of course that opens up a week long from the 20th through the 26th for the distance learning students to actually physically take the exam. Okay, any questions about those deadlines? Clear? Okay, then the next thing we need to worry about is just let me inform you that I have updated some readings and papers on the T-Square site. So in this case, some of the papers I've added for Monday's lecture, I added a reading out of a textbook. I've also updated some readings on the website to cover some of the topics we did the previous week as well. The reading from the textbook, T.S. Rappaport's Wireless Communications. I have an excerpt from chapter 4, and that deals with link budgets, particularly with respect to the cellular link budgets, but it's generic. Wireless is the same no matter what you do in any.
Can I go to the workshop?
Oh, yes. This is the same everywhere, so the link budget is the same. There are ways that he introduces on how to model realistic path loss, some terms that you can add to the link budget to make it more realistic in a cluttered environment, so it's not just free space. I'll mention 2 of them after this just for the point of review because I think they're kind of important to know. So that's the reading. The paper, the reading / notes, and then the paper reading, I have a paper by Pavel Nikitin on RFID link budgets. So you get to see not only just regular link budgets, but some of the backscatter link budgets and how this is a classic paper, one of the most cited ones in the field of RFID. And Pavel's a good antennas and propagations guy, studied under Dan Dansel at CMU, very good pedigree. And he's written some really good papers on this field, so good to learn at the feet of some of the masters there. He's done a good job. Okay. And today's, I've already put, this is for Monday, if you didn't see it already. For Wednesday, today's lecture, the paper that I'm going to have you read is by a guy named Simon Hemour. He was either a grad student or postdoc when he wrote this at Montreal, and he's now an assistant professor in France. But he's talking about RF energy harvesting devices and their fundamental limits. Really good survey paper. Limits and devices. Answers the question, what could you use besides a diode or just a plain old diode to do energy harvesting and rectification from RF? Okay, any questions about the uploaded materials? No? So Rappaport's section, chapter 4 that I've excerpted and placed online for the students in the class to see is considered, that presentation is kind of the gold standard of the cellular industry. His book was the first textbook in wireless communications, and it was published in 1996. It was pretty early on in the game. And that textbook became very widely adopted and is still one of the most commonly used textbooks in the area in the courses in personal and mobile communications, for example. And my old advisor is actually a propagation guy. Like, that's where he got his start. He was making measurements back in the 80s in factories and offices and measuring propagation. And everybody looked at him and said, "What are you doing measuring all this propagation? Like, what good is that for?" And then, so this was the late 80s, and then all of a sudden, he finishes up his PhD, gets an assistant professorship job, and the U.S. government decides it's going to allocate the next generation cellular band. They're going to put PCS at 1900 megahertz, which had never been measured before, at least not in the kind of scenarios that they were talking about, outdoor to indoor, indoor to indoor, lower tier cells, something where the crude modeling that people had done in the past for UHF and VHF propagation just didn't cut it anymore. It wasn't good enough. Well, here comes Ted Rappaport with all this great measurements already and this great expertise for measurements. So it was really good expertise at the right time at the right place, right? And he was able to parlay that into the world's first wireless textbook. So anyway, what I was like this chapter 4 just because it's kind of like the classic presentation from the oldest textbook by the guy that does this stuff like the best and for the longest of anybody out there currently practicing. He's now working at New York University, and he's gotten really big into millimeter wave propagation measurements and modeling. He'd always kind of dallied in millimeter waves, but then got really serious several years ago and published a lot of papers, and has kind of excited the cellular industry about incorporating it into 5G, saying, we think of millimeter waves as sort of a point-to-point technology for the reasons that we talked about last class period, right? You need point-to-point to overcome the propagation losses and the electronics losses, steer two antennas and point them. But, we can use adaptive arrays to kind of get those same effects. And if you can do that, there's actually some benefit to using millimeter waves. You get, when you have arrays and the ability to point, it's better to go up in frequency, which is a little counterintuitive based on how a mobile radio engineer is instructed nowadays. Anyway, just a little bit of background of the people that you read and the topics that we're looking at. The one thing I wanted to point out, he's got a really nice treatment of radio wave propagation, and his version, let's start off with the Friss free space equation. By now you know all the terms by heart. We got receive transmit power in watts, unitless antenna gains, the thing you read off of a spec sheet, wavelength of radiation, separation distance in meters. And I told you last time that we actually like the logarithmic form of this because it turns it into an accounting exercise where you're adding numbers and getting an order of magnitude feel for how big the things are. So you take 10 log base 10 of this, and all the terms fall out like this. Where this is power in dBms or dBWs. Just be consistent on one side of the equation and the other. This is dBi gain, decibel gain, with respect to an isotropic radiator. We call this path loss at 1 meter free space, and we call this free space path loss. This term here. And truthfully, this should be minus. We always want our losses, if they're actually losses, to be positive. And this is free space path loss, the positive number before you negate it. Here we could just write 20 log 10 4 pi over lambda as the path loss at 1 meter free space. And then we subtract that off. We subtract PL when we put that whole positive term in. So it's good to keep your signs straight. And then, of course, you want to add extra losses. Call it excess loss. And there's two things that I'd like for you to pay attention in Dr. Rappaport's article or chapter there. They're kind of two interesting models that make a lot of sense when it comes time to do propagation modeling. One of them is, path loss. When you plot path loss in the dB scale, this is path loss with respect to 1 meter free space. There's path loss beyond 1 meter free space. I go to 1 meter, and then whatever I get on top of that free space path loss is what I record here. And if I plot that in a logarithmic scale, so log transmit receiver separation distance. I do actually 10 log 10. What happens is, okay, the environment is very complicated. There's all these physical mechanisms that cause additional loss in the propagation environment. There are obstacles in the way. You got to go through walls. You got to go around walls. You got to diffract. You got to reflect off buildings. And so the real world here on planet Earth is very complicated, and it winds up being very difficult to predict. So, not surprisingly, if you go around and measure a bunch of path loss as a function of transmit receiver separation distance, you're going to get this huge scatter plot. You get a couple of outliers there too. And one of the ways to model this is, you set this equal to 1 meter here, and this is equal to 0 dB path loss. And then you do a regression analysis, and that's what Dr. Rappaport's book talks about, where you find what's called the path loss exponent that minimizes the mean squared error through there. So the slope, what's the slope of this line, n? And in doing so, you're basically saying in the logarithmic domain, this is path loss with respect to free space. 1 meter free space is 10n log base 10, the separation distance. So what you're trying to do is capture the entire lossiness of an environment with this one value n, the path loss exponent. Now it doesn't look like an exponent in this form, but when you linearize the link budget equation, it looks a lot like the Friss free space equation. Except r is raised to the n power instead of just to the 2, like it would be in free space. And cellular engineers love this because you can do a really simple system-wide analysis with this simple model, and it's pretty accurate. It's not uncommon to get errors as high as 10 to 15 dB of standard deviation, which is a lot if you think about it, right? 10 dB is a factor of 10, 15 dB is like a factor of, I don't know, 50, 30, something like that, 30. That's a lot, plus or minus an order of magnitude and a half. But it turns out that that's usually good enough to design a cellular network. So just with that one piece of information, the path loss exponent, you can capture the behavior roughly of an environment. If I am outdoors and I've got a transmitter on a tower and I'm communicating to a personal device, in this area, my path loss exponent, because of all the high buildings, that fits the data probably close to like 3.5, 4 even. If, however, I move a little bit farther away from the city center with less buildings, maybe more houses and that sort of thing, the path loss exponent drops down to like 2.7. And if I get into relatively flat with some sparse trees, maybe farmland, then path loss exponent can go down to like 2.4 or 2.5. If I go indoors, it shoots back up again. I got all these walls to get through, so things become very lossy. Not uncommon to get path loss exponents of 5 or 6, or even higher. There are some scenarios indoors, however, where you can get path loss exponents less than 2. That's less than free space. How would that be possible? Can anybody think of an environment that would happen in? Where on average you would get more power than free space. Well, what does that really mean physically if I have an path loss exponent less than 2? What that usually means is I have a line of sight from my transmitter to my receiver in this particular environment, and then I also have a lot of additional power on top of that power being reflected or scattered into the area. So in that instance, one common way is I've seen people measure supermarkets for wireless networks. And we think about a supermarket, at least in the US, supermarkets have these metal roofs and kind of tin sides or highly reflective cinder block sides. It's like a big cavity resonator. And you might get some shelves in between you and the transmitter, but there's not solid walls. So you kind of, any transmitter is just going to blanket the area, almost like a reverb chamber with a lot of additional power. And you might wind up getting overall a path loss exponent of 1.4 or 1.7 in that environment. I've seen stuff like that measured before. But this is nice because anytime you change the frequency significantly or change your environmental configuration or just try something new in terms of your environment, whether it's frequency, stuff in the area, you got to go in and remeasure your path loss exponent. And then there's another model. This one's called the Seidel Rappaport model. Where path loss with respect to 1 meter free space is equal to 20 log base 10R, so free space path loss, plus additional factors, number of partitions, and this is partition loss. So sometimes this is called the partition model, although the formal name should be X sub A, the Seidel Rappaport model. And you can have as many of those terms as you like. And this model is interesting because it adds a little bit extra site-specific information. And it gets a little bit better accuracy because of that. You can get accuracies down to like 5 or 6 dB in many instances. It's a lot better than the path loss exponent model. But the price you pay is more complexity. You have to find a way to get more information into your propagation model. So for example, I had a roommate in college, one of my grad roommates in college. His name was Roger Skidmore. He started a company with Ted Rappaport, and he that got sold to Motorola. And their core product was this planning tool that used the Seidel Rappaport model. And he could he could basically suck in a blueprint from a building, for example. Say here's a building. It's got rooms in the building. Here's the blueprint. This is a terrible building. Terrible building. And let's put some trees outside there. And you could drop transmitters and then predict, make a heat map real time, see what you would predict from this system. So for example, if you had a transmitter here and you had a receiver here, what would the Seidel Rappaport model predict? It would draw a line between those, which easy for a computer to figure out distances between points, and then do intersection tests to figure out what type of stuff is in the way. So you would do 20 log base 10, the separation distance, as if this was free space, but then you would add excess loss. You would say, oh, I've got one tree. And trees introduce, on average, I observe a 4.7 dB attenuation per blockage at the frequency that I'm working at. And then I am intersecting one outdoor wall, outdoor brick wall. I find a brick wall, B is 1, and a brick wall introduces about 12.0 dB of attenuation. And I notice I have to go through one interior wall, a plaster wall. Plaster walls maybe only do about 3.7 dB at the frequency that I'm after. And there's only one of those two. So you just subtract off losses based on the type and the quantity of stuff directly between you and the link. So anyway, those are probably the most two important takeaways from that reading that's online in terms of propagation modeling. Does anybody have any questions before we move on? Okay. That's fine. Okay. So let's take a little break from all the equations and analysis and talk about automatic vehicle identification. So the AVI systems have been around for a long time, especially in the proposed form. They really started to be worked on in earnest in the 70s. And the whole idea behind AVI, this encompasses a lot of different applications. We can talk about highway tolling, often called open road tolling, which is what we think about today. But you can also use it to restrict access. Like think a parking deck. And you can use it also for tracking and telemetry. To name just a few. You use it as electronic license plate. And this has been a big success for the industry because it's become very pervasive throughout the world. The first widespread passive version of these RF technologies was deployed over a decade ago. And then before that, they were just very low energy versions, things that would operate off of a coin cell battery, for example, and would last 5 years in the field, 3 to 5 years in the field. You know, you don't want something, if you had to use even today's lowest energy communications, active transmissions like Bluetooth low energy, for example, put a receiver up on a over the highway and then a device that was always transmitting, you would very quickly deplete a battery and you'd have to change it every month or so. It depends on the duty cycle, but a lot more frequently than anybody was willing to do so down at this point in time. And so you find these were also some of the first successful uses of backscatter technology, low energy communications, not just energy harvesting, but backscatter technology. So, what does an AVI system look like? We usually have this thing called a gantry. It's a big superstructure that goes over the road, and you put your transmitter reader antennas here. And you kind of angle it down, and there's an illumination zone. And you engineer the illumination zone so it covers a specific area on the lane. Remember, this is a three-dimensional problem, so you might have a multi-laned highway that you're tolling cars with, and you may need to figure out which lane that they're in, so that you debit the right account and you think the right person has gone through the right lane. And of course, there's all the other components up here. There's often an electronic reader up near the top. There can be a camera. Sometimes the camera just needs to take a picture of the car so that they can mail you a picture of your car when you didn't pay the fine or the toll properly. Other times it's the camera is used to read your license plate and do character recognition on your license plate. It's sort of a backup in case they don't get a proper read off of the RFID tag. And all these are all connected along with other peripherals. To a roadside unit. This is sort of the brains of the operation. This coordinates all the peripherals, the reader, the camera, any other things like maybe a gate that opens up or closes when the proper toll is coordinated, or sometimes there's some inductive sensors to sense the presence of the vehicle. So these automatic vehicle tolling systems are actually quite complicated. There's really multifaceted embedded systems project that require a lot of engineering. And there are only a handful of companies in the world that do that. And of course, the tags on the cars there's a tag. This is supposed to be a car. Tags nowadays actually have the ability to harvest the RF energy. There are several versions and protocols of highway toll tags that harvest the incoming wave and then use modulated backscatter to send back identification information to the reader. And this is a multi-billion-dollar industry. At least the tolls they collect is a multi-billion-dollar industry. This is hundreds of millions of dollar industry in terms of worldwide equipment annually.
The tag is usually behind the car, and then how if it is not illuminated?
Oh, this is a good question. So, where do you put a tag normally?
At the back of at the back, like of the car.
So it depends on where you are. Different tolling agencies have different practices and different types of tags that you can place in different things. So for example, one of the things you have to worry about with this tag is in North America, everybody puts them on the windshield because that winds up being a really nice, kind of angle to cover as you go under a toll tag. And it turns out that RF passes through glass and plexiglass almost losslessly. There's only a slight degradation. In fact, sometimes there's a slight enhancement because you have this thing called pattern sucking. If you put an antenna, a little folded dipole with a chip, if you put that next to a lossless dielectric, the pattern gets a little bigger in this direction and then a little bit smaller in that direction. So you actually can get a little bit of gain if you get the right dielectric up against that. And so that's when it's placed on the windshield. Now there are other worldwide tolling agencies that will put it in other places in the car, or by necessity they'll want to put it on not just maybe a truck windshield, but they'll also want it on the truck trailer that it's pulling. Whereas some people that are driving a motorcycle, here's my hog, and they tend to put it on the gas tank, which is metal. That causes all sorts of propagation problems because you're taking an antenna and you're laying it down on a conductor and essentially shorting it out. You have very bad mismatch losses. No matter how bad you try to, it's almost impossible to undo with matching circuitry. And so this is one of the reasons why they almost always have some sort of camera to do optical recognition on your license plate. Optical recognition on your license plate in and of itself is not the most reliable technique. You get dirt on your license plate and you misread the numbers, or the person drives by too fast, or maybe they took the plates off the car. Or sometimes it's the pattern recognition fails. It's a statistical process. It doesn't always work right. So in that instance, if your optical reader is about 90% reliable and your RFID tag is 99% reliable, then if you put the two together, you're 99.9% reliable. And if you slip through without those pieces of information, then the toll authority just gives up and says, well, I'm not going to collect $1.25 from you. You can keep your 2 yuan. At some point, you got to give up the fight. Okay. Now, what are some of the things you have to worry about when you design these systems? Well, if it's over a highway with a lot of different lanes, oftentimes you have more than one reader, right? Especially if you're doing this maybe at 2 locations close together on both sides of the highway. And there's this thing called reader contention you have to deal with. How do you excite the right tag at the right time and think you're reading the tag that you're exciting? There's this thing called tag collisions. I power up 2 tags, they start talking at the same time. Talk right on over each other. Multi-lane coverage, lane association, the read duration. It was actually a big step in recent years to be able to do this at highway speeds. They used to have this easy pass system in the United States that was not an energy harvesting system, and it still had trouble working at high speeds. You had to slow your car down to 20 or 30 miles per hour as you went under the toll lane, speed back up again. So it was better than coming to a complete stop and having to pay someone, but still, that was not, that seems antiquated by today's standards, where we expect our AVI to work at 80 miles an hour as you blast through the toll plaza. And then, of course, variations. All these different types of tags that you can buy, and then they're user installed. So there's not necessarily uniformity in how they put on the car. Some people just throw them on the dashboard. Some of them are peel and stick tags, and the user puts them in weird angles, wrong polarization, weird places on the windshield. So this is just a small taste of what these systems are like. So I think I'll give you a problem at some point on link budgets on this upcoming homework that deals with an AVI system, how to turn on, power up an AVI system. Do you have any questions? Well, it's 3 minutes till 2 o'clock, so this is about the time that we usually break. So I'll hit the pause button. We'll come back in about 10 minutes, and we'll do exotic devices for energy harvesting. Okay. Now for phase 2 of today's lecture, we're going to talk about this paper that I've uploaded. This is a really nice overview of radio frequency rectifier and devices in general for electromagnetic energy harvesting. Development path and future outlook. Let's talk about what this is. This is written by Hemour and Wu. There are a couple really good graphs here I wanted to talk about, and I want to talk about a derivation that they do in here and kind of explain it in detail because it gets to the heart of energy harvesting. Talks about some fundamental limits, and then some of the devices that you can use in the future. There's a really good historical overview. He's got this picture of a arc radio transmitter from 100 years ago. Oh look, the Kumi graph again. You can't get away from it. The one that I'm most interested in showing you is this plot right here. So I'm going to get some annotations here. Let's see. I am going to, can I draw? Maybe not. Let's just get back to the graph here. This graph is a graph of different devices. So you see here we have on the horizontal axis time, year. Up until the time this paper was written, which this is just about a year and a half ago, 2015, 2014. And each of these lines represents a different type of device that's been used in RF energy harvesting. So of course, what's the one all the way over here? Schottky diodes, that's right. Now, regular diodes have been used too. He doesn't really graph that, because Schottkys generally have lower turn-on voltage, so it cuts right to the more efficient way of harvesting energy. And of course, we've known about Schottky junctions for a long time. Remember, the transistor and the doped diode occur here in the 1950s, late 1940s. But we knew that if you put metal next to a semiconductor, you get a Schottky junction. There's a charge diffusion, barrier regions, nonlinear response that results from the junction of those two materials. And people were making detectors out of those pieces of those electronics as early as the 1900s, 1910s. And you see here on the left-hand side, this logarithmic axis is something that they call zero bias current responsivity. That is a big word, and I'll explain what they mean by that. But what they really mean by responsivity is how curvy is the VI characteristic. Okay. So you have this Schottky diode, and you see things are getting more and more responsive. And it turns out that the efficiency of harvesting, for reasons we'll talk about in a minute, at low power levels is directly proportional to the responsivity, actually responsivity squared of a device. Doesn't matter what you make the device out of. This is the most critical component for measuring how well this is going to be an RF energy harvester at low power levels. So you can see right here we get up, and then about in the 1960s at Bell Labs we figure out how to get highly responsive Schottky diodes, and we hit a barrier. And look at that, nothing changes for years, because as we'll see in a minute, this is kind of a fundamental thermodynamic limit of some of these devices. But of course that's not the only device to be used. There's tunnel diodes, we'll mention those in a bit. MIM diodes, metal insulator metal diodes. Magnetic junction tunneling diodes, or spin diodes as they're often called. And his point in this paper is that there are some of these newer technologies that are rapidly promising to sort of break the barrier when compared to the thermodynamic limit for Schottky diodes. In fact, there's this one point, I don't know if this might come from the author's earlier work or another work. He's written some papers recently on the tunnel diode as a harvester. You see already poking above the thermodynamic limit of the Schottky diode. So that's promising. Anyway, it's a good read. And now I'll switch to a little explanation of a derivation that they do in here that's actually very important. So let's start off with just a regular diode. Here's my diode. And every diode has a VI characteristic, right? Voltage on the horizontal axis, current on the vertical axis. And I can sort of write as a generic diode equation, I is equal to some sort of reverse saturation current times EXP to the input voltage over some sort of threshold scaling voltage minus 1, right? And this gives us a familiar form. Anybody who's studied electronics has seen this curve before. It's this kind of exponential nonlinear response that a diode has when voltage is excited across it. In one direction, it quickly starts acting like a short circuit. In another direction, it quickly has the slope of an open circuit. And here it's kind of somewhere in between. Okay, that's good enough. Now, you'll see this. This is almost like device agnostic. I've just kind of put some physical characteristics here. You could call this the threshold voltage. You could call this the reverse current, reverse saturation current. And sometimes you'll see various forms of this. VT for a Schottky diode, for example. What is this a function of? Well, people have often written this as N times V little t, where we call this the thermal voltage. N is your ideality factor. It's a unitless number, ideally 1. Ideality factor, or sometimes ideality coefficient. And then the thermal voltage can be written as KB times the operating temperature over Q. This is Boltzmann's constant. Which of course is 1.38 times 10 to the negative 23rd joules per Kelvin. This would be the ambient temperature in Kelvin. And of course his ideality factor, so he said ideally that should be 1, and then Q is the charge of an electron. in coulombs. Real quick, give you the value of that so that you can have it in your notes. And that should be it. No, internet's out. You can look it up. Okay, the interesting thing here, of course, is that all of these we actually don't have very much control over, right? We've got Boltzmann's constant. That's a fundamental constant. Nobody's got control over that. Q, charge of electron, you can't change that. I guess you could change the operating temperature, but this is in the Kelvin scale, right? So if we're talking about human temperatures, temperatures that we live at, that's actually a very narrow range in the Kelvin absolute scale, right? Freezing is 273. You know, kind of Shenzhen weather in the summertime is about 300 Kelvin. There's not that much room in between, right? That's a 10% difference at the end of the day. So we really don't have that much control over this thing either. So what does that all mean? So let's say we had our old diode equation. I is equal to IR EXP V over ideality factor thermal voltage. This is part of the proof that Hemour does in his paper. So let's expand this as a Taylor series. Do you remember your high school Taylor series for EXP to the X? That's equal to the sum from n equals 0 to infinity of x to the n over n factorial, right? And from that you can actually just get the Taylor series without doing all that differentiation from that simple series, right? This is basically equal to 1 plus x squared over 2 plus x cubed over 6, etc., etc. And one of the important things to realize about this is that when we talk about energy harvesting in our world, especially low-powered world, x is going to be small. So as a Taylor series, I can take just the first 3 terms of this and get a pretty good estimate of what's going on. So what I'm going to do now is plug that approximation into these first 3 terms here. So I got 1 plus, I have V over N VT. And then I have also over here, okay, that's my linear term. Now I also have the squared term, V squared over N squared, V thermal voltage squared, minus 1. I'm just going to bring down that minus 1. Of course, that cancels with the plus 1 there. So what I really get is I R over NVT times V times 1 plus V over N VT. This guy over here, I'm going to call this 1 over ZD, the impedance of my diode. That's basically the small scale resistance I would see when I put the diode into an AC circuit and give just a little bit of AC across it. It'll look like it has that resistance. But of course, it's nonlinear, so really I can't ignore this last term as well. And the key to this whole analysis is to look at the responsivity, which he defines as basically the second current derivative at some particular bias point. In this case, we're going to use V bias equal to 0.
Professor, where did the 2 come from?
Where did the 2 come from? Was it on the previous slide?
Expansion.
Yeah, that should be part of the Taylor
So
series
it should be-
expansion. Yeah. If you multiply this together, you should get what we had on the previous. Hopefully I didn't drop a 2. Okay. So this responsivity, this is actually the second derivative of current as a function of voltage divided by the first derivative of current as a function of voltage. And you can kind of think of this as quadratic curvature. How curvy is that diode characteristic at a particular point? We're almost always interested in the 0 bias point, where the bias is equal to nothing, because that's what a cold start device would experience. In energy harvesting, you can take electronic devices like diodes and actually give them do something called body biasing. It's like you give a little bit of bias, and in some instances that makes them work better. We're not going to concern ourselves with that, spend a whole course just talking about diodes. We only want to spend the next week or so doing that. Okay, and so what would it be for this Schottky diode? Well, the second derivative and the first derivative of current. Let's do the first derivative of current first. We can just basically eliminate this term here and look at the slope. That's what we called 1 over ZD, or IR, saturation current, over NVT. And up here, if we take the second derivative, we find that that is actually 1 over NVT times ZD. So 1 over ZD, 1 over NVT ZD. Thus, the responsivity, when you divide those two, should be equal to Q over N, Boltzmann's constant, times temperature. We call this responsivity. So 1 over N thermal voltage, and it's really only a function of the ideality factor, which we say is 1, and then these 3 things which we don't have much control over. And that's important because what Hemour shows in this paper is that your RF to DC conversion efficiency eta, so the eta is some number between 0 and 1, 1 being 100% conversion, 0 being nothing, at low powers this is going to be less than or equal to the responsivity squared times the power from your antenna times some factor R naught, which is a function of matching circuit resonance and circuit losses. But this is the real killer here, responsivity squared. We said that the efficiency is related to responsivity squared, and responsivity in the case of a Schottky diode can't be any bigger than Q squared, Boltzmann's constant squared, T squared in the denominator. And that's maybe the biggest takeaway from this paper. Go ahead and read through it. And he's got a sort of a more long, drawn-out proof of this in this historical survey paper. But this results in that thermodynamic limit, what people often call a thermionic limit in energy harvesting. He's got this, that's really what all these equations are. He's deriving that result. So that's the takeaway from this paper. Now there are also some other things, this is for Schottky diodes, right? Which is why we plateau out at a certain responsivity a long time ago. If I could just illustrate the result graphically, what it's saying is that when you have a device at 0 bias, it almost doesn't matter what the device looks like. You could have a device with the following characteristic. At 0 bias, it's really the curviness, that second order curviness, which is what converts RF to DC, right? You think of it as a square law detector. You know, the second derivative of the current diagram divided by the first derivative is really the curviness at that point. And we're limited in a Schottky diode about how curvy we can actually make that point based on physical parameters. The charge of an electron, the average room temperature in Kelvin, Boltzmann's constant, ideality. Those are things that we can't really, either we don't have control over, or we can't really change the parameters of very much. And so what are some of the devices that have more or promising responsivity? Well, there's a whole list in here. I'll give you sort of the high-level version and read the rest for yourself. So we have Schottky diodes. We've actually done as good as we can possibly do with those. We pretty much can design a Schottky diode that operates at the thermionic limit. So these are good, but not getting better. We have tunnel diodes. Now, what is a tunnel diode? Does anybody remember from their electronics class or their physics class, semiconductor class? What's the VI curve of a tunnel diode? Now, how do you make a tunnel diode? Maybe that's the best way to start. You make a tunnel diode by just doping a PN junction, and you overdope it. You put way too many P's and way too many N's on opposite sides. And this makes something called a broken band gap. So in semiconductor physics, you've got two different materials at two different Fermi potentials. By overdoping, you take your P and your N. Here's your P. Here's your N. And you actually make it so that the conduction band of one of your materials is at the same potential as the valence band of your other material. So what happens when in that scenario is that your junction acts like an ohmic junction. You can actually get tunneling where carriers actually go into the band and then jump up to the conduction band in the other material. So here it looks like a resistive device for the tunnel diode characteristic. And then as you raise the potential of this thing and kind of bring these back to more similar potentials, this starts to transition back into a diode characteristic. It looks like this. Let me flatten that out a little bit. It's a little more gradual than this. And so that's the characteristic classic of a tunnel diode. It's a very interesting device because it's highly responsive. This change can happen on the order of tens of millivolts right here. And so that means that the second derivative is very high here, right? It's changing very quickly. And so if you reverse it, it's a little bit counterintuitive, but if you reverse this diode so that you put it in basically backwards, you can actually use this region as an energy harvester. And that's how they did some of those really high efficiency curves on Simon Hemour's paper in that big graph that I showed you. They used a tunnel diode and installed it backwards in the opposite polarity from what you would normally put a regular diode in for energy harvesting. So tunnel diodes, most immediate prospect. For improved energy harvesting. Now, of course, one thing getting in the way is that we are still not very good at making tunnel diodes. The tunnel diode was actually invented, I think it was about 1958 or 59, by a Japanese researcher named Leon Isaki. It was so cool to actually see a device exhibit quantum tunneling for the first time that he got the Nobel Prize for it. However, to this day, it is actually really hard to find anybody that will sell you a tunnel diode. And the reason is, it's actually a neat device because it's got this negative resistance region, which means it makes very good oscillators and amplifiers. You can make reflection amplifiers out of it. You can make oscillators. If you bias it in that negative region, it should become unstable and start to oscillate. However, there is always a cheaper way to do it with, say, CMOS devices, hooking up regular transistors in such a way, biasing them and making them have a negative resistance curve or serving as an amplifier or an oscillator. So it was a novelty. People were very excited in the 60s about tunnel diodes, and it just never really materialized. To this day, if you want to buy a tunnel diode, boy, sometimes, has anybody been to that electronics warehouse in Shenzhen? What did you say? I don't know. Is that what it's called?
The places.
The places? I mean, I've always wanted to go there. I still haven't had a chance to go. Did you go?
Yeah.
You did? Oh, nice. Is it like nerd heaven? I hear you can get like any device on Earth that's electronic there, any component. It's like Radio Shack on steroids. The old Radio Shack on steroids. So, if you go there and look for a tunnel diode, I don't know about the prices here, but in the States you probably won't pay less than $50 per diode. $50, because there are so few of them made. Because they're not used in anything commercial. There's always an easier way to do it with CMOS or just discrete transistors to make something that has a negative resistance curve. Now, why is that? So, and why aren't we doing it that way? The reason comes down to responsivity. It's very easy to make a curve on a VI characteristic that has this shape using active elements. But the responsivity is at least an order of magnitude smaller for the tunnel diode because it's using this quantum tunneling effect. And really it's the little curviness that we get way down here which is going to determine how effective our device is at rectifying. So we're kind of seeing a little, it's cool to use tunnel diodes again all of a sudden. My PhD student, Francesco Amato, just defended his thesis last week. I had to Skype in to the committee. And his thesis was employing tunnel diodes, not in energy harvesting, but in a low-powered communication system that would not have been possible without this device. Maybe we'll spend a day studying that later in the course, but it's kind of a neat experiment that he ran. So it's cool to use tunnel diodes again. That's what it comes down to. And then there's metal insulation metal diodes, or MIM diodes. And these are promising but early. The theory, the physics theory behind these predicts high responsivity, but we haven't been able to build anything quite that high yet. And equally promising but early are these spin diodes that use a combination of tunneling and the spins of electrons to make a nonlinear thing. And that's very similar to the MIM diodes. They're promising but early. And one thing that he's not mentioning in here that we'll probably spend a little time studying is something called an RF thermoelectric generator. Which, when you get to really small scales, we'll learn is actually an efficient energy harvester for RF, or can be. Okay, any questions so far? Okay, well, let me shift gears and we'll do a little prelude to next Monday's lecture. We've talked so far about devices for RF energy harvesting, converting it to usable output power for driving circuits and logic and computation and sensing and all those fun things that we like to do with integrated circuits. So then the next thing we should mention is that that's not the only way to improve the efficiency of a harvesting system. So if you think about an RF waveform, this is how classically we would harvest things. We have a sine wave and it strikes an antenna that goes into some sort of rectifier. And we talked about what rectifiers look like, what kind of diodes could you use in rectifiers. Just kind of scratch the surface. You could spend a whole course simulating rectifier circuits. That would be the most boring course in the world. So we don't want to do that. Now, if I look at this signal on a spectrum analyzer, what do I see? The way I've drawn it here. Yeah, I see a little spike, right? At whatever the RF carrier frequency is. Call it F sub C. So now, there's a little brain teaser. What happens if I have a signal that looks like this on the spectrum analyzer? Two equal valued sine waves, closely spaced, not separated with respect to frequency.
They'll be out of phase signals.
Well, they're different frequencies, so you can put them in phase. Let's say they're in phase, 0 degrees phase offset with respect to one another, just to keep it simple conceptually. So this would be cosine 2 pi fc1t, and this one would be cosine 2 pi fc2t. What would this look like in the time domain?
They'll be overlapped with different wavelength in terms of the expansion.
Yeah. We often say that these two close tones together make a beat frequency, right? It looks like a single carrier wave with a beat frequency. So it'd have an envelope that kind of varied sinusoidally based on the difference of the frequency between here. It'd have a sort of a frequency based on the difference between those frequencies. But then there would be a carrier itself that inhabited the signal. Okay, so then let's change picture. Let's say I have a CW waveform that has the same time averaged power as my double carrier or two-tone waveform. And this is CW. So now let me ask you a question. Which one of these waveforms would be a better waveform to harvest for RF? Which one would convert more power? I'm saying that the average waveform, the RMS average, if I average over a long time, are identical for these waveforms. So both of these have, on average, if you hook up a RF power meter, you would get the same number out of them. So 10 milliwatts, 1 milliwatt, whatever it is. Which one do you think would be better?
The carrier waveform, because it will be of the same frequency.
Mm-hmm. What's the benefit of being at the same frequency? This is kind of getting close to a desired frequency is a beneficial thing in an RF system, because a lot of RF systems are narrowband, right? To get your antenna to work or your rectifying circuit to work, it's probably designed for a specific bandwidth, which truthfully is not going to be very high in most instances. However, let's assume that that bandwidth easily encapsulates these two carriers. So let's take that effect off the table just for a moment. Which waveform would convert better? It doesn't matter which rectifier you pick, but I'll just pick the very simplest half-wave rectifier. Well, let me give a little hint. Don't all answer at once, right? Let me draw on here, say, the threshold voltage of this diode system that I've got. This is the overhead that you have to invest to actually get power out of it. If I drew that threshold line, what do you notice about the difference between those two waveforms?
I think the combined one may harvest more.
Yeah, you're right. You're right. The two tones would harvest more because the CW, at least the way I've drawn it in this example, barely clears the turn-on threshold. I waste all of my voltage turning on the diode, and there's really not that much left over to convert. Over here, this two-tone waveform, so there are some times over here when I get much less than the turn-on threshold to turn that diode on, so I don't get any conversion over here. But most of my energy in the time domain is concentrated near the peak in this waveform, and that should convert more efficiently than the CW waveform. There's a whole field of research out there based on this, and it goes by several names. When you're talking about a single waveform that's designed with this in mind, this is called power optimized waveform. Some people have also studied this effect by looking at multiple CW transmitters. So you've got two RFID readers or two sources of RF power. They're in the same band, but they're not exactly the same frequency. And maybe there's two or more of these. And they add up at a receiver that's harvesting energy, and you get an increase in the percentage of efficiency and gain that you compute. And this is not necessarily a small advantage, because you can play this game for a long time, right? If you have, let's say, 4 tones that are very close together in RF, FC1 through FC4, well, what's that going to look like in the time domain? Well, now you'll have a really high peak. What happens is that the duration of the peak drops, but the peak value itself increases. So you wind up concentrating more and more energy in a smaller period of time if you have more and more synchronized carriers. And you get conversion efficiency gains for that. So there aren't that many systems that actually practice anything like this at the moment. This was an idea that came out of research papers, some of it from our lab, some of it from the lab in Spain. There's a company called PowerCast. They've made a product where you can buy a chip, hook it to an antenna, and you buy another chip or a board from them, and that's their transmitter. And they don't do this, they basically do duty cycling. And it's mostly to get around the FCC laws in the United States. They basically turn the power on high, and then there's a little square wave low power, and then they turn the power on high, because the FCC says, oh, you can only transmit at this average power level. And they define average power as, if you're transmitting digital symbols, you can average over multiple symbols. It's called average conducted power. And so this was originally conceived of as a way to increase the transmit power and efficiency in a circuit without violating the rules of the FCC. In fact, it's kind of interesting. There's always like a high and a low. I said for averaging purposes, wouldn't it be better to have a little bit higher and then off? But it turns out that government regulations, the way that you can compute average conducted power, you can average over bit periods, maybe even multiple bit periods, but you cannot count times when your transmitter is physically off. So that's why there's always a little bit of residual there, just so that if anybody from the FCC checks it, the Federal Communications Commission checks it, they'll be satisfied. Okay, we'll talk about this and analyze it a little more in depth on next Monday. I only gave you a 10-minute break this time, so technically we only have 2 minutes left in the lecture period. This is a good time, just a good place to stop anyway. Have a good weekend.